Okay, so in this chapter, we'll talk about sound waves. Sound waves are mechanical waves. What does that mean when you say they're mechanical waves? They need a medium to travel in. Okay, so sound waves cannot travel in vacuum. So, what kind of medium?
Liquids.
Okay, so sound waves can travel in liquids,
Solids, gas.
solids, and gases. Okay. What you learn is in fluids. What are fluids?
Liquids and gases.
Liquids and gases. Only longitudinal waves can travel. In solids, both transverse and longitudinal waves can travel. Okay. What are the frequencies of sound waves? They can be anything. Your sensor, the sensors you're born with, they happen to work for frequencies of 20 hertz to 20,000 hertz. Okay? And for an old sensor like this probably doesn't work about 8,000 hertz. Okay? His sensor works probably closer to 15,000 hertz. Okay? I'm sorry? Go ahead. What?
Which sensor are we talking about?
Well, your sensors work much better than my sensors.
I'm like 500 or something.
Oh, do you listen to loud music?
Yeah.
Oh, okay. All right. Well, okay. So you broke your sensor. All right. So we're going to talk about. All right. So sound waves is what we're going to talk about. Again, they're mechanical waves, and they travel in material media. Okay, so to produce sound waves, all you need is some kind of diaphragm to vibrate. Okay, some kind of generator to vibrate. Yeah, that's what a speaker does. So you can use anything. You can use your hand and make your hand oscillate like that, and you're generating sound waves. Yeah. Why can't you hear that? Pour that, my friend. Pour that out. You're making too much noise.
Pour it out?
Yeah, on the table. And clean the table after you get done. All right. So why can't you hear this sound?
Because it's outside the range of what your sensors can do.
That's right. So, okay. All right, so all you need is an oscillator. Why do you need this? You need this to pump energy into the system. As soon as you stop doing that, you stop pumping energy, you're not generating any more waves. Okay. All right, so here is an oscillator. And what it does is when it's moving to the right, it produces a high pressure area, a compression, and when it moves away, it produces a rarefaction. Okay, so a sound wave in a gas or in a liquid, in a fluid, is a pressure wave. It's regions of high pressure, low pressure, high pressure, low pressure. And you see if you plot this as a pressure as a function of position, this is what you see, and that's what travels. Okay. Now, if this is a 100-watt speaker, as a speaker oscillates back and forth, it transfers energy into air, mostly as thermal energy. A small part, about 1% of the speaker's energy, goes into compressing and expanding the surrounding air. So only about 1% goes into the sound wave. And 99% is converted to heat. Okay. These compressions and rarefactions move out as longitudinal pressure waves. Okay. And if the frequency of this wave, this is a sound wave no matter what its frequency is, if its frequency happens to be between, let's say, 100 hertz to 15,000 hertz, then your sensor will work. Okay. There are other biological systems. So, for instance, Elephants and whales can hear lower frequency than we can hear. Okay. It turns out that lower frequencies travel further distances. And so some biological systems adapt to that. Okay, so elephants want to be able to communicate over larger distances. Why? Why would elephants want to communicate over larger distances? They're big. They got to eat a lot every day. They got to tell each other where the food is. Okay. Whales, it turns out that in underwater there are channels through which sound waves can travel a large distance, and their calls can travel like in a waveguide thousands of miles. All right. So sound waves in fluids are longitudinal. What does a longitudinal wave mean? What does it mean? So, well, okay, the particles of the medium oscillate parallel to the direction of travel. Okay, that's a longitudinal wave. What is a transverse wave?
Particles oscillate perpendicularly.
That's right. Okay. So, again, this is a transverse wave. Okay, so in a fluid, only longitudinal waves can travel. In a solid, both transverse and longitudinal waves can travel. Okay. So sound waves in most fluids are longitudinal, and sound waves can be both transverse and longitudinal in solids. Okay. All right. So here's a diaphragm, and you're creating sound in this fluid. And you can see that what is illustrated is this is a high pressure area, this is a low pressure area, this is a high pressure area. Okay, let's see what this is saying. This is S indicates the, so in this sound wave, what is oscillating? What is it?
Particles of water.
I'm sorry?
The water is.
This is air, so air particles are oscillating. Okay, so let me go to that. Okay. Okay, so in that oscillation, so here's a diaphragm oscillating, and the air particles are oscillating back and forth like that. Okay, and now what I want to show you is, so those are longitudinal waves. So, okay, so what this graph is telling you is, so here's the air particle, and that's oscillating between there. This distance is S. Okay, so when the air particle is there, S equal to 0. When the air particle is there, S is positive maximum. When the air particle is there, it's negative maximum. Okay, so where the pressure is high, the displacement of the air molecule is 0. Okay, where the pressure is low, okay, no, so where the halfway between, this air particle is all the way to the left, and that's how it's created the high pressure. Okay, and so that's what this graph is telling you. And this air particle is all the way to the right. So these particles are over here, this particle is over here, and the particles that were here are right there. Okay, so that's how high pressure gets created. And this particle got there, this particle goes there, And so this particle, that's how you create low pressure there. Anyway, so that's what this is telling you. And this is the pressure amplitude. See, there's the high pressure, there is the low pressure. And so when a sound wave travels, you can think of it as a pressure wave or a displacement wave. This is the displacement of the air particles. Okay. Anyway, this amplitude is related to this amplitude. Okay. There's the pressure amplitude, and the pressure amplitude is related to the amplitude, maximum amplitude of the molecules of the fluid. Okay. Anyway, you don't have to remember that, but I'm just showing you that there's two ways of thinking about that. Okay. So again, sound waves in fluids are longitudinal, in liquids and air are longitudinal. The sound waves can only travel through material media. Okay. So sound waves cannot travel in vacuum. So all those Star Trek movies where they generate sound, that's not true. Okay. Their speed depends on the property of the medium. The greater you learn, the greater the elasticity, the greater the speed in the medium. So you already saw this. In air, the speed of sound is 340 meters per second. In water, what was it? 1500, very good. 5 times greater. Okay. In steel, you'll see on steel rails, it's about 5,000 meters. Okay. Meters per second. Okay, so anyway, the speed of sound depends on the property of the medium. Okay, wavefronts. What does this mean? What do wavefronts mean? All right, so let me show you what a wavefront looks like. There you go. Okay, so this is a ripple tank, and what's happening is some kind of oscillator is hitting the water surface. Okay, and you see the crests that are generated at the same time, they're called a wavefront. Why do you think we talk about wavefronts?
Because when a wave is traveling, the first time it's traveling through a given medium, that when the wavefront travels through it is the front thing that hits the particles.
So what the wavefront tells us, energy travels perpendicular to the wavefront. Okay. So energy always travels perpendicular to the wavefront. So what's happening to these wavefronts? They're circular. As the circle gets bigger and bigger, what do they look like? They look like a straight line, right? And that's what you're seeing in the ocean. When you go to the beach, what you see is a linear wavefront come at you. Okay? So when a bird sings, what kind of wavefronts are generated?
Circular wavefronts. And
Spherical. Okay, so it's a point source, and the wavefronts are spherical. A light bulb, a point source light bulb, will generate spherical wavefronts. Okay, so energy is traveling. The sun generates spherical wavefronts. Okay.
The sun generates spherical wavefronts from every single point on its surface?
Well, okay, so if you go to large distances compared to the size of the sun, those are spherical wavefront, and then you can think of the sun as a point object. Okay. All right. So we speak a lot loosely around here. Yeah. Anyway, so the point of a wavefront is energy travels perpendicular to the wavefront. Okay. In principle, you can think of any sort of wavefront. Okay. All right. So here's an idealized point source, and it's creating spherical wavefronts, and energy will travel perpendicular to it. Okay. So planar, circular, and spherical wavefronts, among other shapes, are possible. So categories of sound waves. We classify sound waves from our perspective. Okay. So from our perspective, so our sensors our idealized sensors can, in principle, hear from 20 hertz to 20 kilohertz. Okay? And so any frequency below that is called infrasonic wave. Any frequency above that is called ultrasonic wave. Okay? So there are biological systems that are sensitive to those frequencies. So again, like large animals are sensitive to lower frequencies. Bats use higher frequencies. Okay? A dog whistle, for instance. What does a dog whistle do? Have you ever heard a dog whistle?
No.
It's like
No.
it's very high pitched.
So it produces a frequency higher than 20 kilohertz. Again, obviously, the dog is sensitive to that. Yeah. So here's an interesting economic lesson. Teenagers can hear frequencies of 10,000 hertz and above. But guys like me cannot hear them. So what's the point in putting that here? So here's an example. So if you go to a mall and go to an expensive store, this is how they keep the teenagers out. They'll play a sound of high pitch, which is annoying to teenagers, and they don't stick around. But the paying customer, they don't hear it. So apparently this is done. So, but the flip side of it is kids have done this in the class. They'll have a high-pitched ringtone on their phone. The teacher can't hear it, right? And kids call each other. Have you guys done that? All right, so she admits to the crime. All right. So, anyway, all right. So, here's a range of frequencies and phenomena that you come across. We'll talk about this more. Okay. So anyway, so these are the frequencies you can hear, and infrasonic waves are sound waves of frequency less than 20 hertz. Ultrasonic waves are sound waves of frequency greater than 20 kilohertz. Okay. So speed of mechanical waves, speed of sound waves. Okay. Speed of the wave depends on the elastic property divided by an inertial property. Inertial property is related to the mass. Okay. And elastic property, so there are three kinds of elastic properties: bulk modulus, shear modulus, and tensile modulus. So for mechanical waves, what matter are bulk modulus and shear modulus. Okay, and in fact, for fluids, only bulk modulus matters. Okay. So speed of sound in fluids is equal to the square root of the bulk modulus divided by the density. Okay. And so here's speed of sound in various media. And I'll bring your attention to a few speeds that you'll need to know. So the speed of sound in air at about 20 degrees Celsius, speed depends on the temperature, is 340 meters per second. Yes, sound will travel from here to Mainland High School in 1 second. Okay. In water, it's 5 times greater, 1,500 meters per second. In iron, it's 6,000 meters per second. So on train tracks, it'll travel 6,000 meters per second. So you can go down to the train tracks in Daytona, hit the tracks with a hammer, and you can hear it in Ormond Beach in 1 second. Yep. All right, so here's the speed of sound in air. Okay. The temperature dependence is important. So this is gamma. You'll learn about this in physics 2. Is the ratio of specific heats. Again, the ratio of specific heat at constant pressure to constant volume, R times This is the temperature in Kelvin scale, and that's the molar mass of air. Okay, again, you don't have to remember any of the details. Here's the speed of sound as a function of temperature in the Celsius scale. So the speed of sound in air is 330. This is all at sea level. Okay. So this is the speed of sound at 0 degrees Celsius, and per degree rise in temperature, it's 0.6 meters per second per degree Celsius. Okay. All right, so here is just a little fun fact. Let's see, here's the speed of light, 300,000 kilometers per second. Here's the speed of sound in kilometers per second, 0.3 kilometers per second. Okay. So essentially, light travels 1,000,000 times faster than sound. Okay. So if you see a flash of lightning, the light gets to you almost instantaneously. Okay. And then the sound follows, the thunder follows. Okay. 1,000,000 times slower. Okay, so how far away is lightning? The 5-second rule. Each 5-second, okay, so if 5 seconds passes before you hear the thunder, the lightning was a mile away. Okay. If you hear the thunder 10 seconds afterwards, the lightning was 2 miles away. Yeah. And so on. That's what that means. We learned that all waves carry energy. Yeah. Something is pumping energy into the medium, and that energy is being carried away by the medium in a wave. Okay. So the piston transmits energy to the elements of the air in the tube. The energy is propagated away from the piston by the sound waves. Okay, so this formula is just like what you saw for the string. The string was carrying away energy. Okay, so the sound waves are carrying energy away. Okay, and what this formula tells you is you can stand anywhere, and how much energy is passing you per second is the power. Okay, and that's what's given here. So it's equal to 1/2. Rho is the density of the fluid in which the wave is traveling. A is the area of cross section. V is the velocity of sound, and omega is the frequency of sound, and S is the amplitude of the air molecules. Okay, a more useful thing to do would be to give you the pressure amplitude, and we'll give that to you later. It's only written in terms of the molecular amplitude just because this formula looks simpler, and it looks similar to the formula for the string. Yeah. So here's the intensity, power per unit area. Power per unit area is the intensity, and that's given in terms of the pressure amplitude. Okay. So it's the pressure amplitude divided by 2 rho, the density of fluid, times the velocity. So intensity of a point source. So if you have a point speaker, the intensity would be the power. So this could be a little birdie singing, and if you're that far away, the intensity of the sound reaching you is I is the power emitted divided by 4 pi r square. What is this 4 pi r square?
It's the area of the wavefront of the sphere.
So the surface area of a basketball. Yeah. Yeah.
Sure. What did you say that was called? The letter? It's,
This one?
yeah.
That's power. It's just a script P.
Okay.
Yeah. So the intensity is the amount of energy reaching you per second per meter square. Yeah. Okay, so now here's a very interesting thing. All right, before we go into these slides, let me ask you this question. You guys are all very smart. Okay, so this guy's playing a violin. Okay. Now I want to hear it twice as loud. What should be done? So he's going to play at a certain level. He's also going to play at the same level. How loud do I hear it?
Twice as loud.
Twice as loud, right? Everybody agree? Your ears are built such that 10 people need to play at the same level before you hear it twice as loud. Okay, so it turns out your sensors are built like, okay, so let's say 10 to the power 1.
Algorithmically.
Yeah, so your sense of loudness is built logarithmically. It's proportional to that. Okay? So if you want to hear it 4 times as loud, how many violin players have to play?
10 to the fourth.
No, 100. 2 times 2. Okay. 100. So now you understand in those orchestras why you have 30 violinists and stuff like that. Okay? So that's what's going on. Okay. Same thing with, let's say, hotness. Okay, so let's say you put a drop of hot sauce on your tongue. It feels a certain amount of hotness. To feel twice as hot, you have to put 10 drops. Okay? Okay. All right, so your sensitivity is logarithmic, okay? And so we define a decibel scale. Okay, so here are these numbers. Humans can detect intensities in the range of, intensity is the amount of energy falling per second per unit area. Okay, so this is the smallest intensity you can hear. That is the softest intensity you can hear. The loudest sound, this is how our friend there ruined his hearing. You listen to too much of that. Huh? Is, well, that's the intensity, and that corresponds to 120 decibels. Is that what you did? You listened to a lot of, or you're not hearing me? What's that? What's that? Yeah. All right, so you see the intensity is a trillion-fold increase. So this is the softest you can hear, and this intensity is a trillion-fold greater before it starts hurting. Why have you evolved like this? You don't want to die when you hear lightning, but you also want to hear a predator, the softest sound a predator makes. You know, so that's why you have to have a range of hearing. Yep. But I mean, so if you perceive this to be a trillion times louder than this thing, you're wasting too much CPU. So you don't want to do that, okay? So minimize, so to make efficient use of your CPU, you just say your brain thinks this is about 5,000 times louder than that. So that's why we evolved that way, okay? So that's why we define this decibel scale, okay? So the decibel scale is the intensity of sound divided by the threshold of hearing times log of that, okay? So what we are essentially doing is we are picking out this portion. Your sense of loudness depends on the exponent, okay? And that's what the decibel scale is related to. Yeah. So the threshold of pain is this intensity hertz, 1 watt per meter square, and that corresponds to a decibel level of 120 decibels. threshold of hearing is 0 decibel. Okay. You hear a 0 decibel sound. An increase in sound level by 10 dB, 10 decibels, corresponds to increase in sound intensity by a factor of 10. Okay, so if one violin is playing and then 10 violins playing, the decibel level has increased by 10. Okay, so as a rule of thumb, doubling in loudness is approximately associated with an increase in sound level by 10 dB. Okay, so doubling in loudness. Your perception of loudness doubling corresponds to increase in intensity by a factor of 10. Okay. Here are various sound levels in decibels. Okay, nearby jet plane is that's jackhammer, machine gun, and all that. So all those people operating all those, they always use mufflers. Okay. Mosquito buzzing is 40 decibels. Okay. Noise pollution can contribute to high blood pressure, anxiety, and nervousness. So yeah, that's high noise pollution is a serious occupational hazard. Okay, again, the sensors you're born with is they're pretty slick. Okay, so the human ear has tremendous range and sensitivity. You already saw that it has a trillion-fold sensitivity to intensity. Okay, so you can hear a trillion-fold intensity range. Okay. The perception, so now we'll talk about other features. The perception of frequency is called pitch. Okay. Typically, humans have an excellent relative pitch. So if the frequency differs by 0.3% or more, you can detect that. Okay. So what that says is if you're listening to 100 hertz and the frequency, somebody changes to 100.3 hertz, then you can sense the change in pitch. You go from 500 to 501.5 hertz, you can sense that change in pitch. Yeah. Loudness, if you can discern differences in 1 decibel in 1 dB. So 20 dB and 21 dB will sound louder to you. Yeah. Now, this is how you define the decibel scale. Okay, this is I naught is the threshold of hearing, which is that. This is I naught, and I is the intensity. Okay, when you use an instrument, what this is measuring is I is watts per meter squared. Okay, an instrument will just accurately measure this. It doesn't care about the frequency and stuff like that. But your ears are sensitive to frequencies. Okay, different frequencies are perceived as different loudness. Okay, so here's an instrument. Okay, so the sound level in dB. Here's an instrument measuring 100 dB at all these frequencies. It doesn't care what the frequency is. But the sensor you're born with, at higher frequencies, the intensity doesn't need to be as high to perceive the same loudness. Okay, so for around these frequencies, okay, the intensity can be lower and you'll perceive as a loud sound. Yeah. So when you were kids and the doctors did a hearing test, this is what they were testing. Okay, they were measuring these curves, so they would do the test for various frequencies. Okay, so this white area is where you can hear. Okay. So here's an interesting point, okay, your ears are most sensitive to about 3,500 hertz. Okay, so that is the frequency at which you can hear the softest sound. Okay? So if you want to hear sounds at lower frequency, the intensity, the sound level has to increase before you can hear. So 100 hertz sound has to be at 30 decibels before you can hear it. 3,500 hertz can be at 0 decibel and you can hear it. Okay? And that's what that means. So sonars use those frequencies and so on. Okay, so let's do 2 more slides and then we'll quit. Okay. So interference of sound waves. Now so here are 2 speakers, for instance. Okay, this speaker is producing a sound wave. This speaker is producing a sound wave. And now, so let's say this speaker is sending out this wave, and this speaker is sending out this wave. Okay. So what these points are is, okay, so the blue is purely constructive interference, purely constructive. Purely constructive. These are purely constructive and purely destructive. Okay, so here the sound is canceling on the black spots, and on the blue and red spot they're enhancing each other. Okay, so when both the waves reach with a crest at a given location, they'll add, and when one wave reaches with a crest and the other reaches with a trough, then they'll cancel each other. Okay.
When the sound waves are canceling each other, can you not hear it at all?
No, you can't hear it at all. So we'll charge you $500 for these concert tickets. This particular frequency will cancel at your spot completely. Okay, so that's why these stereo speakers are 180 degrees out of phase, and the center aisle is canceling. All frequencies are canceling. Okay. So just hang on 2 seconds. So you can see there's destructive interference and constructive interference are the peaks. Okay. That's constructive interference and destructive interference. So these speakers are in phase. So if this was an auditorium, you wouldn't want to put your seats there for this particular frequency. Okay. All right. So in this business, what this is the path difference. So one wave traveled that distance to get to that point, and this wave traveled that distance. And the difference, absolute value of the difference in the 2 paths is called the path difference. Okay? And if the path difference happens to be an integer multiple of the wavelength, then you have constructive interference. If it happens to be a half integer multiple of the wavelength, then you'll have destructive interference. So if the path difference is 3 wavelengths or 4 wavelengths, you have constructive interference. And if it's a half a wavelength difference, then you have destructive interference. Okay? So this is a very important phenomenon, and you have to be cognizant of this kind of stuff when you're an acoustics engineer. Okay? All right, we will stop here, and I will finish this lecture on Wednesday and then do problems and finish it on Wednesday. And you have the option of taking the test either next Monday or Wednesday. Okay?